Okay, so this is Faraday's law example. Assume a loop enclosing an area A lies in a uniform magnetic field. The magnetic flux through the loop is phi b, and that is equal to BA cos theta. B is the magnetic flux density, A is the area of the loop, and cos theta. So cos the theta is the angle between the field lines and normal to the loop. The induced EMF is E is equal to minus d by dt BA cos theta. So yeah, so this is just repeated. So the induced voltage is equal to, we can take the n outside because n is a constant. So it equals minus n d by dt brackets BA cos theta. Right, so if we look at this example here, AC generators can be understood using Faraday's law. The graph below shows how the flux linkage varies in a sine wave as a square coil with 1000 turns and a side length of 20 centimeters is rotated in a uniform field of flux density 0.8 Teslas. Now, this looks like y equals sine x, right? Y equals sine t. If you were to differentiate this, you get dy by dt equals cos t. But remember, of the Lenz's law, it becomes minus cos t. So cos t is this. So minus cos t will look like this, right? Okay, because the equation for EMF is minus NBA over T. So you're finding out the rate of change is the rate of change. Now the fastest rate of change is here, right? But it's negative. But because of the negative, it becomes positive. So the fastest rate of change is going through here. That's why the maximum is here. Another greatest rate of change, because the slope is the greatest, is here. It's going in a positive direction, but it is minus because of Lenz's law. So therefore, it goes here, right? So minus, plus there. And here the gradient is 0, so therefore it passes through here. The gradient here is 0, so it passes through here. So therefore you have a minus cos t graph. The coil rotates by 15 degrees in 2 seconds. Calculate the induced EMF. So remember, this is the equation, and we do need to put a cos theta in here. So here it needs to be cos theta. Right, so we know n is 1000. We know b is 0.8. Convert 20 centimeters into 0.2. So times by 0.2 squared times by cos 15, and then all of that divided by t, which is 2. Right, so on the calculator, 1000 times 0.8 times 0.2 squared times cos 15, and then divided by 2, I get 15.45. So 15.45 volts, and I think they rounded it to the nearest number. Right, a surge coil has 4,000 turns and a cross-sectional area of 1 centimeter squared. Given that it induces an EMF of 2 volts when removed from the field in 1 millisecond, calculate the flux density. Right, so again we can use EMF equals minus NBA over T. So we know that the EMF is 2, so that is equal to minus 4,000 times, we want to work out B, times by B. 1 centimeter squared is 10 to the minus 2 squared, so that's 10 to the minus 4. And time is 1 millisecond, so that is 10 to the minus 3. Just rearrange. So B is equal to 2 times 10 to the minus 3, divided that by 4,000 times 10 to the minus 4. So that's 20 over 4,000, and that is 1 over 200, and that is 5 milliteslas, I think. So 5 milliteslas. Let me check. So 1 divided by 200. Yes, that's 5 times 10 to the minus 3. State Lenz's law and explain why it is a statement of energy conservation. The direction of the induced EMF current opposes the action that caused it. If Faraday's law did not have the minus sign, then electrical energy would be created when the magnet and coil of opposite polarity were brought together. So therefore you're creating energy out of nowhere when no work is done on the magnet. F. Explain using Faraday's law why large current carrying coils can be dangerous if the current is suddenly switched off. Solution. Large coils are linked by their own field. If the current is switched off, then the magnetic field collapses, creating a large change in the flux linkage over a short time period. Because if you do EMF equals MBA divided by T, when T is very, very small, you create a large EMF. So if T is very small, the backward EMF is very large.